In this lesson, we are looking at chemical bonding. The physical forces that join atoms together are called bonds. We are going to be looking at two kinds of bonds, ionic and covalent. The smallest particle or basic unit of an ionic compound is an ion. The smallest particle or basic unit of a covalent compound is a molecule. Molecules are neutral particles that consist of two or more covalently bonded atoms. Paired molecules are called diatomic molecules because they are made of two atoms. Therefore, the smallest parts of matter are atoms, ions, and molecules. I'm going to write that down. The smallest parts of matter are ions, atoms, and molecules. If we consider pure substances, they can be broken down into two categories. A pure substance can be either an element or a compound. The smallest part of an element is an atom. Compounds can be of two types, ionic compounds or molecular compounds. Ionic compounds form when a metal and a non-metal bond, and the smallest component is an ion. Molecular compounds form when two non-metals bond, and the smallest component is a molecule. Chemical bonds are the physical forces that hold two atoms together, and there are two general types. The first type, called ionic bonding, involves electron transfer. Ionic bonds form when valence electrons are transferred between metals and nonmetals. For example, let's consider the bond that forms between calcium and two fluorines. First of all, calcium has an atomic number of 20, so I am going to shade in this outer circle because that orbital should actually be there. Oops. When calcium forms an ion, it will lose the electrons in its outer shell to have a full inner shell. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. On to the next shell. 11, 12, 13, 14, 15, 16, 17, 18. I'm going to stop there, write it down as 2 plus for an ion charge, meaning that it has lost 2 electrons. It lost the 2 electrons that would be in the next shell. In fact, it gave them to fluorine. Fluorine has an ion charge of -1, meaning that it gains 1 electron. Fluorine has an atomic number of 9, so it has 9 electrons on its own. I'm going to fill that in on each of these fluorine atoms. So 2 in the inner shell. That leaves 1, 2, 3, 4, 5, 6, 7 on the next shell. Then I'm going to show the electrons that each fluorine atom got from calcium. And each fluorine will have a charge now of 1 negative because it has gained 1 electron. This is calcium fluoride. It's a compound that is added to toothpastes to prevent tooth decay and strengthen enamel. We're going to be comparing the properties of ionic and covalent compounds. Ionic compounds form crystals. You may be familiar with salt crystals. NaCl is table salt, sodium chloride. Usually the crystals of ionic compounds are large enough to be seen. If you look at a grain of table salt, if you poured some out and looked at it, you could see the actual individual crystals. Ionic compounds also have very high melting points. That's because the crystal structure here is very organized and very tightly bonded together, and it requires a lot of energy to break those bonds. This temperature here of 800 degrees Celsius, that's the temperature that table salt melts at, and that is a very difficult temperature to reach in lab conditions. Ionic compounds are also hard and brittle. The tight arrangement of atoms prevents ionic solids from bending, so this leads to fracture. Ionic compounds conduct electricity when they're dissolved in water. Because in water, the ionic compounds will dissociate into their ions, and the ions will be free to move about and can therefore conduct the electricity. Now we're going to look at covalent bonding. Covalent compounds form between two nonmetals. So I'm going to write nonmetal plus nonmetal. Here's an example of carbon dioxide. In covalent compounds, instead of transferring electrons, they share electrons. So nonmetal and nonmetal share electrons. Oxygen has an atomic number of 8, has 8 electrons when it's neutral. Carbon has 6. So I'm going to draw carbon 6 electrons. Now it has 2 in its inner shell, it's full. It only has 4 itself in its outer shell, and I'm going to draw them like this. Because we know that each oxygen has 8. It has 6 in its outer shell, and it's wanting to gain 2. I'm going to draw oxygen's electrons on. Perhaps I should have done that first. Here's 2. Then I'm going to draw 1, 2, 3, 4, 5, 6. Same with this one. 2 in the inner shell. 1, 2, 3, 4, 5, 6. Now if we look at each of them individually for a minute, this oxygen has 8 electrons in total in its outer shell if you get to count these 2 as well. And you do because it's sharing it. Same with this oxygen over here. Carbon in the middle has 4 of its own plus 4 that it's sharing because it's sharing with 2 oxygens. This is carbon dioxide. We keep talking about the magic 7, the 7 diatomic molecules. Oxygen never just is O by itself, it's always O2. And so it shares 2 electrons with another oxygen molecule. So there's the 6 that that oxygen has by itself. Put on the 6, or sorry, 8, but 6 in the outer shell. Here's the electrons that this oxygen molecule has. And now that they're sharing, they both have complete outer shells. It's the attraction of the negative charges of the electrons, and that negative charges are attracted to both nuclei, because both nuclei have protons in it, positive charges, and that's what holds covalent compounds together. So in covalent molecules, the atoms are held together by the attraction of the shared negative electrons to the positive nuclei. We're going to look at some properties of molecular compounds and contrast this and compare it to the ionic compounds. Similar to ionic compounds, the molecular compounds also form crystals. But the crystals here aren't so regularly structured. The crystals here can be of varying shapes. The atoms aren't in fixed positions, as they are in ionic crystals. You may be familiar with water crystals, with snowflakes, and you know they come in many different shapes. Molecular compounds have low melting points, low melting and boiling points. And that's because the attractive forces between the covalent molecules are weak, so they're easy to separate. They're poor conductors, so they do not conduct electricity. This is different than the ionic compounds. So a good lab test, if you weren't sure if a compound was ionic or covalent, would be to dissolve it in water and see if it conducts electricity or not. Molecular compounds do dissolve, but they don't dissociate, so they don't form ions. So we'll write that here. They dissolve, but they do not form ions. And that's the end of today's lesson.